In the last video, we introduced the three of the fundamental subspaces for a matrix: the row space, column space, and null space. And now we want to talk about how do we find a basis and then also, of course, the dimension for those new subspaces. We'll first focus on the row space and column space, and we'll start with the case where the matrix that we're talking about is in row echelon form. So if B is in row echelon form, then a basis for the row space of B consists of the rows in the matrix B with a leading 1. A basis for the column space of B consists of the columns with a leading 1. Okay? So let's take a look. Here, this matrix here, B, is in row echelon form. Notice it's not reduced row echelon form. For instance, let's look at our leading ones. Circle our leading ones. Here's our first non-zero entry in that row, first non-zero entry in that row, first non-zero entry in that row, first non-zero entry in that row. Right? So this matrix has 4 leading ones. Clearly, this leading one does not have zeros everywhere else. Same with this leading one and this leading one as well. And so this is not reduced, but it's row echelon form. So it doesn't matter what we do. Very simple. To find a basis for the row space of A, we can simply take the rows in the matrix with the leading 1 in it. That would be the first, second, third, and fourth row. So a basis for the row space of B consists of the first row. And I'll write these in comma delimited form. It's just easier. Second row, third row, and fourth row. And those are all 6 tuples, and there it is. This is a basis for the row space of B. What is the dimension for the row space of B? That's the easy part, right? How many vectors do we have? Let's count them up. 1, 2, 3, 4. Dimension 4. And notice the row space of B is a subspace of 6 space. Why? Because these are all 6 tuples. They reside in 6 space. So, but the dimension of our subspace is 4, which it should be, right? The dimension of the subspace is always less than or equal to the dimension of the vector space, which in this case, the vector space 6 space has dimension 6. This is not the only basis for the row space of B. Again, there's infinitely many. And you can imagine there's other row echelon forms. They will all have, though, remember, row echelon forms always, for a given matrix, will have the exact same location for the leading ones. Those are fixed. Okay. Now, reduced row echelon form, we would get zeros above the leading ones, right, by adding appropriate multiples of those rows to the pivot row or the leading 1 row. And so we could put this in reduced row echelon form. In that case, I'd get a slightly different basis, but it would still have 4 vectors in it. Okay. What about a basis for the column space? Well, same thing, column space now. A basis for the column space of B consists of the columns with the leading ones. So in this case, that's the column, what? The first column, the second column, the fourth column, and the 6th column. Just say it's the first, second, fourth, and 6th columns of B. So let's write that out. Now the columns are 5 tuples, if you'll notice. I'm going to still write them as comma delimited form. If you want to write them as a 5 by 1 column vector, that's another way you could write them. Just easier to write it across the paper with the amount of screen space that I have with this camera. So the first column was that. The second column in comma delimited form is this. The fourth column, right, which is 0, 4, 1, 0, 0. And the sixth column, 50210. And what is the dimension of the column space? How many vectors in the basis? 1, 2, 3, 4. Okay. So there we have it. There is our basis for our row and column space. Now, one thing you might be interested in or observed or think about is the dimension of these two subspaces was the same. They both were 4. Will that always be the case when we're looking at a matrix that's in row echelon form? Will that always be the case? You should be able to answer that. Answer, yes, because, right, the 4 is really coming from the fact that there are 4 leading ones, right? Since the basis for the row space consists of the rows with the leading ones in it, there's 4 rows, and the basis for the column space consists of the columns with the leading ones in them, there's 4 columns, right? So the dimension for the row space and the column space will be the same if the matrix is in row echelon form. What if the matrix is not in row echelon form? Will this be true? The dimensions of the row and column space be the same? Answer, yes. Okay, but we need to look at this case. How do we find the basis for and dimension of a matrix that is not in row echelon form? Well, what if we took the matrix and put it in row echelon form? Okay. What can we say about the process of doing those row operations? Remember the row operations, interchanging any 2 rows, adding a multiple of one row to another, or multiplying a row by a non-zero constant. What can we say about that process? How does it affect the row, column, and null space of a matrix? Well, I'm glad you thought about that because that's what we're going to talk about right now. So finding a basis for the row space and column space of a matrix not in row echelon form. Okay. So first of all, performing elementary operations, the 3 row operations I just talked about on a matrix, does not affect the row space or the null space. Now we know it doesn't affect the null space. Why not? Because when you're talking about the null space, you're talking about the solution space to AX equals 0. And how do you solve that solution space? You take the augmented matrix and you do row operations to it. You put it in row echelon form or reduced row echelon form. You are doing the row operations. And that's not going to affect, right, the solution to the system, which is the solution space, the null space is, again, the solution to the system. Set of all vectors in the solution to the system. Now, the row space of A is also not affected. Now, let's see if we can talk about this. So let's see. Obviously, let's see, if I have a matrix A with rows 1 and row 2, right? Then if I have a vector in the row space of A, it could be like row 1 plus row 2. Let's say there's 2 rows. Let's just make it easy. 2 rows in the matrix A, all right? If this is my vector, let's call it vector B, all right? Now, if I interchange, so if I now say interchange the rows, right? So if I interchange the rows, that means row 1 new, let's see, row 1 new, we'll do, that's the new row 1. This is the new, the little asterisk will be the new one, is just the old row 2. And the new row 2 is just the old row 1, right? And so V is now what? Can I still write it? It's row 1, which is what? New row 2, right? Row 1, right, was the new row 2. And row 2 was the new row 1, right? So obviously swapping the order doesn't change anything, right? We can still write V as a linear combination of the rows after a row swap, okay? So that's interchanging rows. What if we multiply? What if we say, multiply, let's do row 1, and we'll multiply it by let's make it up. Let's multiply it by 4. 4 times row 1 becomes the new row 1 here. The new row 1, okay? And let's say that our vector v is, let's just say it's 3 row 1 plus 2 row 2. Let's just say that. Okay, so here's v in terms of the row 1 and row 2. What are our new ones? So the new row 1 is 4 times row 1, but our row 2 star, the new row 2 star is the same. That doesn't change, right? That's still row 2. So can I write this in terms of that? Well, how many row 1 stars do I need? How many row 2 stars do I need? Okay, well, row 2 stars is easy because row 2 star is the same. It hasn't changed. We needed 2 row 2s before. We still need 2 row 2s. Right? These are the same. They're equal. But here, right, I need 3 row 1s. Right? How many row 1 stars will that be? Well, if there's 4 row 1s equals essentially row 1 star, right? Then 3 row 1s would be equal to what? How would I get this to be? How do I get a 3 here? I would have to multiply by what? 3/4. Right? What's 3/4 times 4? That's 3. But 4R1, that's equal to what? 3/4 times what? 4R1 is the R1 star. So that's what I need. That's the adjustment I need. I need to now take 3/4. So I can still write V as a linear combination of the new rows, right, after I do this multiply row by a constant. So I can still do it. I just need a new variable there. So again, the vector V is in the row space of this new matrix. Now the last one is if I take a multiple of one row and add it to another. So let's take row 2 and let's add, I don't know, 3 times row 1 to it. And that becomes the new row 2. Okay, so that's what we have. And row 1 is the same as row 1 before. That's not changed. Okay, so let's say we have V again is 3 row 1 plus 2 row 2. Okay. Now V is equal to, let's do A row 1 star plus B row 2 star. So can I do this? Can I find A and B that's going to work that's the same as this? Well, again, we see row 1 is the same here, and row 2, what do we need this to be? We need this to be, well, let's go ahead and write it out, right? Row 2 is actually what now? This is, the new row 2 is now row 2 plus 3 row 1, right? So what do I have here? This is what? Just A times row 1, right? Because the row 1 doesn't change. So what do I got? Combined like terms, I got A row 1 plus 3 row 1. That's A plus 3 row 1, right? A plus 3 row 1. Plus what? Oh, I messed up. Sorry. Excuse me. Times B. So this is A row 1. Let's do B row 2 plus 3B row 1. Now let's combine like terms. A plus 3B plus B. Okay. All right, so we're matching this up with this up here, right? Match it up. What does B need to be? Pretty obvious, right? B needs to equal 2, right? What does A need to be? Well, A plus 3B, B is 2, right? So we're going to stick that in for that. Has to equal what? What's the coefficient of R1 have to be? 3. So A plus 6 equals 3. What does A have to be? Negative 3. Okay, so bottom line is, I'm going to take negative 3 of the new row plus 2 of new row 1 plus 2 of the new row 2, and I get the same vector V. Bottom line is, this is showing that no matter what row operation I do to the matrix A, the new matrix I get the row space of that matrix is going to be the same as the row space of the original matrix A. So any row operation is not going to affect the row space. Okay. So if you didn't follow what I did here, that's okay. Just know that performing row operations on a matrix does not affect the row space of A or the null space of A. Okay. The problem is, though, the elementary row operations may affect the column space of A. And so let me give you an example. Here's a matrix A, and if I put it in reduced row echelon form, here it is. You can kind of see that obviously I can get there in one step because the second row is just in proportion to the first row. Right? I do -2 times row 1 added to row 2, I get to here, right? And that's the reduced row echelon form. So the column space of A is the span of what vectors? The vector 1, 2, or that column vector, and the vector 3, 6. Now, what's an example here? The vector 4, 8 is in the column space of A. Why is that? Because 4, 8 can be written as a linear combination. In fact, just add one of the vector of each one of each one, and I get 4, 8, right? So if I just add the two columns together, I get this. So this has to be in the column space of A. Okay? Well, is the vector 4, 8 in the column space of this? Let's call this matrix the B, the reduced row echelon form. Is this in the column space of B? No. This is not in the column space of the reduced row echelon form of A. Right? Because the span of this is what? The span is 1, 0 and 3, 0. Can I add any linear combination of these two vectors and get 4, 8? Is that going to happen? Am I going to be able to get that 8? Am I going to be able to get that 8? No way, right? And so you see what happens is the column space can't be the same, right, for the matrix A and its reduced row echelon form in this case. And because of that, we have to be careful when we're looking at taking a matrix, putting it in row echelon form, and talking about then a basis for the column space. So what are we going to do? You know, so this tells me that when I'm going to find the row space for a basis for the row space of the matrix A, I can just find the row space for a basis for the row space of its row echelon form, like we did previously. Right? Just find what? The rows with the leading ones in them, right? It'd be the same. That would be the same. But for the column space, we cannot necessarily do that. So what can we do? This is what we're going to do. We're going to use this theorem, which I'm not going to prove, but if A and B are row equivalent matrices, what's that mean? One's obtained from the other by a series of elementary row operations, right? Doing our elementary row operations. Then a given set of columns of the matrix A form a basis for the column space of A, if and only if the corresponding columns of B form a basis for the column space of B. So there's the connection. Corresponding columns. So when I take a matrix and put it in reduced row echelon form, if I want to find, take matrix A and find a basis for its column space, and I put A in a row echelon form, or say it's reduced row echelon form, whatever, then the basis for the column space of A will come from the columns of A that correspond to the columns that are the basis for the reduced row echelon form, or the row echelon form, as the case may be. Okay, let's do an example, see if this makes any sense. So some of you might be, what does this mean? Let's do an example. So let's find a basis for, and of course the dimension of, the row space, column space, and null space. So here's the matrix. It is clearly not in row echelon form. I'm going to go ahead and give you the reduced row echelon form of the matrix. It's here. Okay, so let's look at just, if I was talking about just this matrix, how would I find a basis for the row space? The row space would be, let's circle our leading ones, would be the first, second, and third row, right? Dimension 3. What would a basis for the column space of this matrix here on the right, the reduced row echelon form of A be? It would be columns 1, 3, and 4. Okay, But how do I find a basis for the row space and column space of matrix A? Is it the same as over here? Well, for the row space it is. A basis for the row space of A, right? Since the row space of any matrix is not affected by the row operations, we just went through that long process, then the row space of this matrix and the row space of this matrix are the same. So I can find a basis for the row space of matrix A by simply finding a basis for the row space of its row echelon form, which is again what? First, second, and third rows of this. Oops. And what's its dimension? 3. Now, what about a basis for the column space? This is what we were just talking about, basis for the column space of A. Well, remember, when we do row echelon forms, that can affect the column space. In fact, I know that the column space of my matrix A is not the same as the column space for this matrix. Right? What's the column space for this matrix? What's a basis for the column space? It would be the first, second, as far as first, third, and fourth columns, right? The ones with the leading ones. But just look at any linear combination of these columns. Is it possible to get, for instance, the first column in this matrix? Is this first column is clearly in the column space of matrix A, right? This first column is definitely, any column in the matrix is automatically in the column space, right? Just take one of this column and zeros of everything else. So this is in the column space. This first column is in the column space of A. Is this first column in the column space of this matrix? Is this first column here in the column space of this matrix over here on the right? Clearly not. Every column has zeros for the last two entries. There's no way you're going to take a linear combination of these 5 columns and get this vector here, right? This 5 tuple with the 1, 2 at the bottom here. So clearly they're not the same. So what do we do? Remember what it said? It said corresponding columns. So the first, third, and fourth columns of this matrix form a basis for this matrix over here on the right. But the corresponding columns over here, which would be again the first, third, and fourth columns of the matrix A, right? Of the matrix A over here, form a basis for the column space of it. And so those columns are 1, 3, 4, 1, 2. That's the first column. The third column, so -1, 1, 1, 0, 0. And the fourth column. And what's the dimension of the column space? It's also 3. 1, 2, 3 vectors. And so as we say, that obviously, you know, these leading ones are the key to the dimension for the row space and column space. They will always both have the same dimension. But notice the row space in this case, well, in this case the row space and column space are both subspaces of 5 space, because this is a 5 by 5 matrix in this particular case. Okay. Could I find a basis for the row space where the vectors come from the original matrix A, come from the rows of A? Well, you can't do the same thing and say, hey, corresponding rows form the same basis. In other words, you can't say these 3 rows form, first, second, third rows of this matrix form a basis for this matrix. Therefore, the first, second, and third rows of this matrix form a basis for the row space of A. You cannot say that. And here's the basic reason why. It is because if I'm doing row operations, one of the things I can do is I can interchange 2 rows. Okay, so I might interchange 2 rows here, and then, you know, combine the rows down here in such a way that I get these rows of zeros. And initially I could have 2 rows that are, you know, something like scalar multiples of each other. They can be linearly dependent. So this first, second, and third row could be linearly dependent upon each other. Okay, that's a possibility, and so we cannot do that. Okay, we cannot do that. We will show you a way, though, a little bit later, or talk about a way where you can find a basis for the row space of A consisting of the rows of A. So notice right now the basis for the row space of A consists of the rows from its reduced echelon form. Okay, the other thing was to do the null space, and I want to do the null space of A. What's a basis for and dimension of the null space? So remember, the null space of A equals the solution space of AX equals 0. Keep in mind, this is the A, right? This is not the augmented matrix. These are not constants. These are the coefficients of the variable. There are 5 variables: x of 1, x of 2, x of 3, x of 4, x of 5. So don't forget, if we're talking augmented matrix, right, for the system AX equals 0, you've got to include that row of zeros there. So be very careful here. There are 5 unknowns. And what do we have? We have x of 2 and what? X of 5. Those are free variables, x of 2 and x of 5. So I'm going to let x of 2 be a parameter and let x of 5 be a parameter. And then I just write out my first equation: 1x of 1 plus 2x of 2 minus x of 5 equals 0. And so I can solve for x of 1, our fixed variable, subtract 2x2 or 2r, add x of 5 or add t. Second equation, x of 3 plus 2x of 5 equals 0. Solving for x of 3, our fixed variable, negative 2x of 5 or negative 2t. And the last equation with a leading one says x of 4 equals 0. All right. So we have done this before, right? We're just solving the system. And what is it? It's a ordered triple. X of 1 is what? Negative 2r plus t. X of 2 is what? R. X of 3 is negative 2t. X of 4 is 0. X of 5 is t. Then we're going to break this up. Do you remember how we do this? I've got what? R times what? Negative 2, 1, 0, 0, 0. Plus t times what? 1, 0, negative 2, 0, 1. So I hope you understand we've done this at least a couple other times. And if I go ahead and scalar multiply and then add these vectors, I get back to this. What are we saying? The null space is any vector of this form. The null space of the matrix A is any vector of this form, and therefore these two vectors span the space and they are linearly independent, and therefore they form a basis. So the basis for the null space of A, or A basis again, is negative 2, 1, 0, 0, 0, and 1, 0, negative 2, 0, 1. This is A basis, right? What's the dimension for the null space? 2. Dimension is 2, because there's 2 vectors. Okay, got one more thing to talk about, and then in the next lecture we're going to look at the relationship between these fundamental subspaces of a matrix and actually introduce a few others. But just have you notice, some of you could deduce some relationship between the dimension of the null space of a matrix. Right, think about where that 2 came from. I'm sort of pointing out things that may be of interest to you. Where did that 2 come from? What type of variables are these? Okay, relationship between the dimension of the null space and the dimension of the row or column space. Where do these numbers come from? Okay, is there a relation? Is there something you can always say if you have a given matrix and you know the dimension of, say, the row space or the dimension of the column space? Could you deduce the dimension of the null space directly from that? And you can. And we'll talk about that a little bit later. I want to just show you a real neat application in closing for this. Suppose I have a set of vectors, and these vectors reside in 4 space. And I want to talk about the subspace spanned by these 5 vectors. They're all 4 tuples, right? So notice, since there's 5 vectors in 4 space, which is dimension 4, what do we know about these 5 vectors? We know they are linearly dependent. So I want to find a subset of these 5 vectors that forms a basis for the subspace that is spanned by these vectors. In other words, if I take any linear combination of these 5 vectors, it will form a subspace of 4 space, right? And I want a basis for that subspace. But again, the basis cannot consist of all 5 vectors because these 5 vectors are linearly dependent, right? Since the dimension of 4 space is 4, any collection of 5 or more vectors will be linearly dependent. So how do we do this? Here's what we do. We are going to put these vectors in as columns of the matrix A. Right? So I'm going to create a matrix A, and I'm just going to slide in these as the columns. And if you really think about the fact that matrix multiplication can be thought of as a linear combination of the columns of A, that's really all we're doing here. That's the idea that we're going to be using essentially. V1, V2, V3, V4, V5. All right? And then what I'm going to do is I'm going to find a basis for what? Well, the space spanned by these 5 vectors is the same as the space spanned by these 5 columns of A. And what is that space? What is the space spanned by the columns of A? What is this? What do we call that? The column space. So how do I find a basis for the column space of A? We just did it in the last example. We do what? We take this and put it in a row echelon form. I'll do reduce row echelon form. And I get 1, 0, 0, 0. And I will circle my leading ones. Okay. So what is a basis for the column space of A? Is it these 3 columns where the leading ones are? No. That would be a basis for the column space of this matrix, right? But remember, it's not necessarily, and in fact it can't be, a basis for the column space of our matrix A, which is what we're looking for, right? What is it though? The corresponding columns, right? So it's going to be the first, second, and fourth columns of A. So 1, negative 2, 0, 3, 2, negative 5, negative 3, 6, and 2, negative 1, 4, negative 7. Right? And what are this is V1, this is V2, and this was V4 from the original set. So guess what? The space spanned by those 5 vectors that we were given is the same as the space spanned by the column space of A. So it's the same vector space. So since a basis for the column space of A can consist of these 3 vectors, then the answer is up here to our question. Find a subset of these vectors that forms a basis for the subspace of 4 space spanned by these vectors, and the answer is v1, v2, and v4. And further, what else do we know? We know that the dimension of this subspace is what? 3. So it's a neat little useful tool. If we have a given set of vectors, we can find a basis for the dimension, a basis rather for the subspace that they span. Okay, so we will, in the next lecture, we're going to look at some more relationships between these fundamental subspaces of a matrix, and we're going to learn some really cool new words. I'm excited.